1.6 Dalton's atomic theory. Although the origin of the idea that matter is composed of small indivisible particles called atomato, meaning indivisible, dates back to the times of Democritus, a Greek philosopher 4060 to 370 before Christ. It again started emerging as a result of several experimental studies which led to the laws mentioned above. John Dalton 1776 to 1884. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following: 1. Matter consists of indivisible atoms. 2. All atoms of a given element have identical properties, including identical mass. Atoms of different elements differ in mass. 3. Compounds are formed when atoms of different elements combine in a fixed ratio. 4. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination. However, it could not explain the laws of gaseous volumes. It could not provide the reasons for combination of atoms, which was answered later by other scientists. 1.7 Atomic and molecular masses. After having some idea about the terms atoms and molecules, it is appropriate here to understand what do we mean by atomic and molecular masses. 1.7.1 Atomic masses. Mass of an atom is actually very small because atoms are extremely small. Today we have sophisticated techniques, example mass spectrometry, for determining the atomic masses fairly accurately. But in the 19th century, scientists could determine the mass of one atom relative to another by experimental means. As has been mentioned earlier, hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1 without any units, and other elements were assigned masses relative to it. However, the present system of atomic atomic masses is based on carbon 12 as the standard and has been agreed upon in 1961. Here, carbon 12 is one of the isotopes of carbon and can be represented as 12C. In this system, 12C is assigned a mass of exactly 12 atomic mass unit AMU, and masses of all other atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12th of the mass of one carbon 12 atom and 1 AMU. equal to 1,66056 into 10th power 24 minus 24 gram. Mass of an atom of hydrogen equal to 1.6736 into 10th power 24 gram. Thus, in terms of AMU, the mass 1.6736 into 10th power minus 24 gram by 1.66056 into 10th power minus 24 g of a hydrogen atom equal to 1.0078 AMU equal to 1.0080 AMU. Similarly, the mass of oxygen minus 16 160 atom would be 15.995 AMU. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculation, we actually use Avogadro average atomic masses of elements, which are explained below. 1.7.2 Av- uh, Average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, present occurrence, the average atomic mass of that element can compute, computed. For example, carbon has the following three isotopes with relative uh, abundances and masses as shown against each of them. Isotopes. Isotope relative abundance percentage atomic mass AMU 12C 1998 98.892 12 13C 1.108 13.0035 14C 2 into 10 power minus 10 14,00317. From the above data, the average atomic mass of carbon will come out to be 0.98892 12U plus 0.01108 13.0035 plus 2 into 10 to 12 14.00317 equal to 12.11 Similarly, average atomic masses of other elements can be calculated. In the periodic table of elements, the atomic masses mentioned for different elements actually present their average atomic masses. 1.7.3 Molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains one carbon atom and four hydrogen atoms, can be obtained as follows. Molecular mass of methane CH4 equal to 12.011 U plus 4,1,008 U equal to 16.0443 U. Similarly, molecular mass of water H2O 2 equal to 2 into atomic mass of hydrogen plus 1 into atomic mass of oxygen equal to 2 1.008 U plus 16.00 U equal to 18.02 U. 1.7.4 Formula mass. Some substances, such as sodium chloride, do not contain discrete molecules as their constituent units. In such compounds, positive sodium ion and negative chloride ion entities are arranged in a three-dimensional structure as shown in figure 1.10. It may be noted that in sodium chloride, one Na plus ion is surrounded by 6 Cl minus ion and vice versa. Figure 1.10, packing of sodium and chlorine ion in sodium chloride. The formula, such as sodium chloride, is used to calculate the formula mass instead of molecular mass as a solid state. Sodium chloride do not exist as a single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chloride equal to 23.0 U plus 35.5 U equal to 58.5 U. Problem 1.1. Calculate the molecular mass of glucose C6H12O6 molecule. Solution. Molecular mass of glucose C6H12O6 equal to 6 12.00011 U plus 12.1008 U plus 6 1600 U equal to 72.066 U plus 12.096 U plus 96.00 U equal to 180.162 U. 1.8. Mole concept and molecular masses. Atoms and molecules are extremely small in size and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote one dozen for 12 items, score for 12 20 items, gross for 144 items, we use the idea of mole to count entities at the microscopic level, that is atoms, molecules, particles, electrons, ions, etc. The SI system mole symbol mole was introduced as seventh base quality for the amount of substance. The mole symbol mole is the SI unit of amount of substance. 1 mole contains exactly 6.0014076102 elementary entities. This number is the fixed numerical value of the Avogadro constant Na when expressed in the unit per mole and is called the Avogadro number. The amount of substance symbol N of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, a, an ion, an electron, any other particle or specified group of particles. It may be emphasized that the mole of a substance always contains the same number of entities, no matter what the substance may be. In order to determine this number of precisely, The mass of carbon 12 atom was determined by a mass spectrometer and found to be equal to 1.992648 into 10 to the power minus 23 gram. Knowing that 1 mole of carbon weighs 12 gram, the number of atoms in it is equal to 12 gram by mole 12C by 1.992648 into 10 to the power minus 23 gram by 12 catom. 6 0.221367 into 10 power 23 atoms or mole. This number of entities in one mole is so important that it is given a separate name and symbol. It is known as Avogadro constant or Avogadro number, denoted by Na, in honor of Amedeo Avogadro. To appreciate the largeness of this number, let us write it with all zero zeros without using any power of 10. 6.000221367000000000000. Hence, so many entities, atoms, molecules, or any other particle constitute one mole of a particular substance. We can therefore say that one mole of hydrogen atoms equal to 6.022 into 10 to 3 atoms. 1 mole of water molecules equal to 6.022 into 1023 water molecules. 1 mole of sodium chloride equal to 6.022 into 10 to 3 formula units of sodium chloride. Having defined the mole, it is easier to know the mass of one mole of a substance or the constituent entities. The mass of one mole of a substance in grams is called its polar mass. The molar mass in grams is numerically equal to atomic or molecular or formula mass in U. Molar mass of water equal to 18.02 gram per mole. Molar mass of sodium chloride equal to 58.5 gram per mole. 1.9 percentage composition. So far, we were dealing with the number of entities present in a given sample, but many a time information regarding the percentage of particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question you would ask it is what is its formula or what are its constituents and in what ratio are they present in the given compound. So for known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. In other words, one can check the purity of a given sample by analyzing this data. Figure 1.11, 1 mole of various substance. Let us understand it by taking the sample, uh, taking the example of water H2O. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated as follows: mass percent of an element equal to mass of that element in the compound into 100 by molar mass of compound. Molar mass of water equal to 18.02 gram. Mass 1% of hydrogen equal to 2 into 1.008 by 18.02 into 100 equal to 111118. Mass percentage of oxygen equal to 1600 by 1802 into 100 equal to 88.79. Let us take one more example. What is the percentage of carbon, hydrogen and oxygen in ethanol? Molecular formula of ethanol is C2H5OH. Molar mass of ethanol is 2 into 12.01 plus 6 into 1.008 plus 16.00 G equal to 46.068 gram. Mass percentage of carbon 24.02 gram by 46.068 gram into 100 equal to 52.14%. Mass percentage of hydrogen equal to 6.048 gram by 46.068 gram into 100 equal to 13.13%. Mass percent of oxygen equal to 16.008 gram by 46.068 gram into 100 equal to 34.73%. After understanding the calculation of percent of mass, let us now see what information can be obtained from the percent composition data. 1.9.1 Empirical formula for molecular mass. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, or whereas the molecular formula shows us the exact number of different types of atom present in a molecule of a compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can further be obtained if the molecular mass is known. The following example illustrate this sequence. Problem 1.2. A compound contains 4.07% hydrogen, 24.27% carbon and 71.65% chlorine. Its, its molar mass is 98.96 gram. What are its empirical and molecular formula? Solution. Step 1. Conversion of mass percent of to gram. Since we are having mass percent, it is convenient to use 100 gram of the compound as the starting material. Thus, in the 100 gram sample of the above compound, 4.07 hydrogen, 24.27 gram carbon and 71.65 gram chlorine are present. Step 2. Convert into numbers moles of each element. Divide the masses obtained above by respective atomic masses of various elements. This gives the number of moles of constituent elements in the compound. Moles of hydrogen equal to 4.07 gram by 1.008 gram equal to 4.04. Mole of carbon equal to 24.27 gram by 12.01 gram equal to 2.021. Moles of chlorine 71.65 gram by 35.43 gram equal to 2.021. Step 3. Divide each of the mole values obtained above. Divide each of the mole values obtained above by the smallest number amongst them. Since 2.021 is the smallest value, division by it and given a ratio of 2 is to 1 is to 1 for H is to Cl is to Cl. In case the ratios are not whole numbers, then they may be converted into whole number by multiplying by the suitable coefficients. Step 4. Write down the empirical formula by mentioning the numbers after writing the symbols of respective elements. CH2Cl is thus the empirical formula of the above compound. Step 5. Writing molecular formula. A. Determine empirical formula mass by adding the atomic masses of various atoms present in the empirical formula. For CH2Cl, empirical formula mass is 12.01 plus 2 into 1.008 plus 35.453 equal to 49.48 gram. B. Divide molar mass by empirical formula mass. Molar mass by empirical formula mass equal to 98.96 gram by 49.48 gram equal to 2 equal to n. C. Multiply empirical formula by n obtained above to get the molecular formula. Empirical formula equal to CH2Cl n equal to 2. Hence, molecular formula is C2H4Cl2. 1.10 Stocho, sto- Stoichiometry and stoichiometric calculation. The word stoichiometry is derived from two Greek words, stoichio, stoichion, stoichion meaning element and metron meaning measure. Stoichiometry thus deals with the calculations of masses, sometimes volumes also, of the reactants and the products involved in chemical reaction. Before understanding how to calculate the amount of reactants required or the products produced in a chemical reaction, let us study what information is available from the balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation of this reaction is as given below. CH4G gram plus 2O2 gram gives CO2 gram plus 2H2O gram. Here methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products are gases in the above reaction and this has been indicated by letter gram in the brackets text to its formula. Similarly, in case of solids and liquids, S and L are written respectively. The coefficient 2 for O2 and H2O are called stoichiometric coefficients. Similarly, the coefficient for CH4 and CaO2 is 1 in each case. They represent the number of molecules and moles as well taking part in the reaction or formed in the reaction. Thus, according to the above chemical reaction, 1 mole of CH4 gram reacts with 2 moles of O2 gram to give 1 mole of CO2 gram and 2 mole of H2O gram. 1 molecule of CH4 gram reacts with 2 moles of CO2 gram to give 1 moles of CO2 gram and 2 moles of H2O gram. Double 2.7 capital L of CH4 gram G reacts with 45.4 capital L of O2 small g to give 22.7 capital letter L of CO2G and 45.5 L capital L of H2OG. 16G of CH4 G reacts with 2 into 32 G of O2G gram to give 44 gram of CO2 G and 2 into 18 gram of H2OG. From these relationship, the given data can be interconverted as follows: mass, mole number of molecules, mass or volume equal to density.